Thank you. So my name is Igor. I'm a postdoc at Stockholm University in the group of Josefin Olkruna. Our collaborator is also Malte Brack from Kiel University. And I will talk about the Stokes problem, well-posedness under pressure, Dirichlet boundary conditions, which sounds a little bit boring. So I will try to spice it up with what we are actually interested in. So we are interested in the cryosphere. Cryosphere? The cryosphere are all regions around the globe that are covered in ice. So you can think about Greenland, for example. That's a continental ice sheet. Okay, so Greenland and Antarctica are our computational domain. And the main question is how to make ice sheet simulations run faster. So there are several different models that are coupled together to perform an ice sheet simulation. And the first one I will start with is the free surface equation. Consider that this is a 2D slice of Greenland. And what we are typically interested in ice sheet simulations is how this upper surface moves in time. How does it deform? So the movement of the upper surface of the ice sheet, the free surface, is governed by this advection type equation. But to solve this, so we have our h is the upper surface, and the domain where we solve this equation is this omega perpendicular. But to solve that, we need the surface velocities, u1, u2, and u3. And this is more or less the main topic for today. To get the velocities over the surface of the ice, we solve the Stokes model in the volume of an ice sheet. This is the Stokes problem. What is interesting with this is that this is a nonlinear Stokes problem. The ice is modeled as a non-Newtonian fluid. So this viscosity here is nonlinear, following some power law. The challenges with this model is that it's expensive to solve, especially because we are dealing with transient simulations, and we are interested in simulating ice sheets long time in the future. So a remedy a remedy to shrink the cost is to neglect a few stress terms on the premise that an ice sheet is thin, and make the viscosity linear. In that way, we derive the shallow ice approximation model. You can think about the relation between the Navier-Stokes and the shallow water approximation model. It's similar here with ice. And then we get the shallow ice approximation model, which is fairly similar to the Stokes problem, except that this stress term here, so we only have the mixed stress term. And the viscosity is linear. It does not depend on the velocity itself anymore, which gives the whole problem then is linear and computationally inexpensive. But the challenges with this model are that the accuracy of the velocities that you compute is only good in some parts of an ice sheet and not in the others. And the remedy is to solve that model where accuracy is good, but solve this one, the Stokes problem, elsewhere and do the coupling. And this is not exactly representative for which are the accurate regions for the shallow ice approximation model. But the point is that over this 2D slice of Greenland, we, for example, want to solve the shallow ice approximation everywhere because it's so cheap to compute. But then we want to, in particular, resolve for the velocities in this Stokes region over here, where we impose the Dirichlet boundary conditions from the shallow ice approximation model when computing the solution of the Stokes problem. So the sub-problem formulation, the Stokes one, is the following. We are looking for the velocity in H1 and P in L2 such that this holds, as I said, with the shallow ice approximation velocities and pressure. And the main question is that problem well posed, if you do it like that? But let's take a few steps back first. The problem that we will actually look at is a linear Stokes problem, formulated like that, with homogeneous Dirichlet boundary conditions in both velocity and pressure. And we observe that this pressure term over here, it's with integration by parts, it becomes this. We have a gradient of pressure, and then it is relevant to when determining the well-posedness of this problem, in particular, focusing on the pressure part. to study the kernel of the gradient operator. So the pressure is actually unique up to a constant when no boundary conditions in the pressure are imposed. So whatever condition we impose on the pressure, it has to make the gradient of P non-zero over the whole domain, or at least in some parts of the domain. The question is, does this condition that we're prescribing over here always make gradient of P non-zero in some parts of the domain? So let's chase a counterexample to that. Let's assume that pressure actually lives in that pressure is a constant, and consider this one-dimensional real line. So this is a real line. I throw over a domain. This is like a domain omega, and I have a constant defined over the whole real line. When I intersect the real line with omega, I see that the pressure there is constant. The gradient P is zero on omega, and this is not good. So now let's follow this. We want to impose a zero boundary condition on the pressure. Remember that the pressure lives in L2, so I am allowed to I can allow a jump discontinuity anywhere. And the boundary I consider now is just this left boundary. So if I impose this zero boundary condition through this jump discontinuity, open interval here, closed here, I still get that the gradient of P is equal to zero, which is not good. That means that this is a counterexample, that this will not work. But then how to make it work? Again, now do consider that P is a constant, but instead impose a zero boundary condition in a delta region close to the boundary. So this is the delta region that is a subset of omega. Now gradient of P is not equal to zero anymore. In fact, it's a Dirac distribution in this point, which is measurable in the H2 minus 1 norm, and this is what we will use later on. So this delta saves the day. But we can mimic what we actually want to do with this delta, because we can shrink delta and shrink it again, and we can shrink it almost to an arbitrarily small region, which will then do almost what we want, and that is require pressure to be zero at the boundary. So we formalize this. We have the Stokes problem. We're finding U in H01 and then P in this L delta, such that this holds, but then P is zero on this delta. And then the pressure space becomes this. This space is actually complete. That is possible to prove. So instead of imposing the boundary condition here, we impose it in this delta region. And our analysis is also valid for when you want to impose the pressure inside the domain, like in a small delta region. Okay, what we build our analysis on is on the following observation. So this problem is actually well posed if you don't impose this, but you impose that the integral of pressure is equal to zero over the whole domain. So for that, you define this space. And the key ingredient when you show the well-posedness of the problem with pressure living here is the Netchas inequality. It's like a Poincaré inequality, but for L2 functions. So you have the gradient of Q measured in the H2 minus norm over here. And what we work on is an extension to that. So we use that, but extend it from L02 to L delta 2, where our pressure lives. What we observe is that each Q in L2 can be made zero average through this operator T. It's an average subtracting operator. So the idea one is to take a Q from L delta 2 and then map it to L02 through this operator T. And because Q lives at L delta 2, TQ will live at L02, we can use the Netchas inequality that I mentioned before. So like that. But then idea two is to bound T from below. And to do that, you have to show that T is continuous, injective, closed range. And then you arrive to something like that. So then you have that the pressure Q is bounded by these two constants times gradient of Q. And that holds for each Q in L delta 2. How to do that, I will not talk about. But in the end, we derived a well-posedness estimate. So let's make a following observation. This estimate is good, but in the worst case, this C0, actually, it depends on the delta. It depends on the volume of the delta, and it depends on that in a bad way. So C0 over delta depends on the volume of the delta, square root of the volume of the delta. If we send this volume of the delta, we make the region thinner and thinner, then the inverse of that constant will go to infinity with slope 1/2. And the question is so this smells of an issue, but is it really an issue in practice? What are the practical implications? So let's go back to our model coupling. Now I will try to mimic this model coupling between shallow ice and Stokes, but in a more simplified way. We will solve Stokes over the whole omega, over this whole square, and we get out velocity and pressure, and then we will solve Stokes over a subregion, this one, using the boundary conditions obtained before, but also perturbed. And we will vary the magnitude of this perturbation a bit to see what happens. So the question we pose is, how are we doing with this norm of P in practice if we send H to 0 and if we send the volume of delta to 0? So remember, delta is this region that we will be shrinking. This is one of the solutions, unperturbed exact solution. It looks like that. We have velocity, horizontal, vertical pressure. Then we couple. So you should, over here, there is a sub-problem. And then both solutions are merged together. So they are pretty good. The solution is coupled with delta, an empty set. That means that the pressure is actually enforced totally on the boundary. The solution looks very good over here. There is no problem. I should mention that we are looking at the small perturbation. So the boundary conditions are subject to a very small perturbation, almost 0. Then we couple the solution again, but we take 8 layers, diameter of delta to be 8 layers around the boundary. And we still see that everything is fine. But then we perturb a little bit more. Now we have a large perturbation of the boundary conditions on the sub-problem here. And then we look at the pressure enforced directly on the boundary, enforced in 8 layers around the boundary. So this pressure here is discontinuous. That doesn't disturb me so much because it lives in L2. It can be. But what disturbs me is that this discontinuity actually carries over to the velocity. So the velocity lives in H1. This is not allowed. What we see here is a boundary layer. But then when we increase this delta to 8 layers, we see that first, this jump discontinuity is better behaved, but also this transition over here is smoothed. So increasing delta certainly helps. And if we look at the error distribution only in the vertical velocity, for example, when P is just straightly enforced on the boundary of this sub-problem here, we see that the gradient here is very sharp. But when we increase delta, first of all, the gradient gets less steep, and the error actually decreases. So that's a good sign. Now we look a little bit at the convergence plots. So what I want to show is that when the diameter of delta is 0, pressure directly on boundary of omega, we get the growth in the norm of P as H goes to 0. This is not good. This is not a sign of well-posedness. If we increase delta, for example, to 2H, the growth is still there, but it decreases, and then it becomes constant at some point. But the point here is to make the diameter of delta H independent. And if we do that, then we get constants here. And this is what we're after. And yeah. Okay, and just to mention that the 1/2 growth of the constant, we have been able to reproduce it also in practice. So yes, for a large perturbation in the boundary conditions, your norm of P will grow with the power 1/2 as the volume of delta goes to 0. To conclude, the Stokes problem with Dirichlet boundary conditions is well posed if you include the delta. I think that this result is not known from before. As delta to 0, then the norm will blow up, but imposing pressure on d omega is not really tragic in practice as long as h is not super small. However, imposing p on delta subset omega is far more robust. The suggestion is to impose p on delta, and importantly, where the volume of delta is independent of h. Yeah, thank you.